Okay, in this video I'd like to review graph movement, or how we can graph these quadratic functions using the vertex form, and discuss how two different equations might appear differently. And then also I want to review domain and range. There were some questions on that last week, and I felt that Math Excel did a decent job of explaining what they are when you used the Help Me Solve This, but some of you still had some questions, or maybe didn't realize that the tools were available to help you with that. So in this video that I'm recording today, I'm actually going to reference another video online that I've linked to in Schoology. And let's see if this will play on this screen too. Okay, now that I've resized the window, let's play this video, and I'll pause and add my comments as needed.
Welcome to Friendly Math 101. Today our lesson is on finding domain and range of quadratic functions. Let's take a look at our first example. Just to review, our domain represents all x values of our function, and the range will represent all the y values of our function.
So what she means by that is that if you think of all of the coordinates, the infinite number of points that land on this function, this U-shaped graph, imagine where all of those coordinates are. If you think of all of them listed out in order, what x values would we see in that function's coordinate list, and what y values would we end up seeing there? Now, we did talk about this in class a little bit last week, but I'll let you continue watching the video here to hear her description.
So if we're looking at this parabola, this U-shaped graph, we have to understand some characteristics of it before we list out our domain and range. So looking at these arrows at the bottom of our parabola, it represents two different things. This arrow here represents that the graph goes forever down and also to the left. I'm going to exaggerate that arrow a little bit. And this arrow means our graph goes forever down and to the right. So if we're just talking about our x values, we could say that our domain is a set of all real numbers because our graph includes every single positive, negative number out there, including all those decimals and fractions in between.
So she's using this symbol here, double bar R, I sometimes call that, to represent all real numbers. And again, what she's saying is that if you can imagine a real number on a number line here, not an imaginary number, not a complex number, but any number that you could imagine exists somewhere on this horizontal number line. And if you can imagine that number, if you can picture that number in your head, then it will show up as an x-coordinate somewhere on this graph. So if I'm thinking of the number -3, for example, well, here's -3 on the x-axis, and if I look up, well, that coordinate there would contain an x value of -3. Looks to me like a -3, 4 would be the coordinate, but the -3 is the x value that shows up in that graph. -4, -5, -6, and so on. If I wanted to jump out here to positive values like 5, 6, or 7, I don't see them in the graph currently, but since this graph does continue down and to the right infinitely long, or infinitely far, at some point I will see a coordinate way down below that does have an x value of 5. In fact, any real number, any number that we can perceive along this x-axis will have a coordinate associated with it somewhere on this graph. Now, the range that she'll describe in just a second is talking about the y values. And my question for you to think about before I press play again is what are the y values? What are the y coordinates that we'll see in that list if we were to list out all of the coordinates of this graph? Will we see all real numbers in that list?
Our range, on the other hand, has a definite limitation. If we're looking at our vertex here, the highest y value of our graph is here at +4, and everything beneath +4, because remember, these arrows go down forever. And so, to describe our range, we could say the set of all y values where y is less than or equal to 4. It does include 4 because 4 is where the vertex is.
Now she's using this set notation, we call that. The braces, we call these. Capture the whole group, and if you heard what she said the range will be all y values such that y is less than or equal to 4. When we write this, or when we see some multiple choice quiz questions, I believe we'll just use this component of that set notation. We'll just say that the range is the y values that are less than or equal to -4. So here again, if I imagine all of the coordinates that exist in this particular graph, if I focus on their y components, the y coordinates themselves, the largest y value that I'll see in that coordinate list is a +4, and that occurs right here. There is no point on this graph, there's no coordinate in this graph that contains a y value of 5 or 6 or 7 or 8. The graph doesn't reach that high. There's no y value that even includes 4.1 or 4.001 or anything like that. 4 is the exact largest value, and it is included in our list, but it's kind of the boundary, if you will, here. So all y values beneath that will exist somewhere in the graph, but nothing above that point.
Or the max. Let's take a look at another example. So again, I'm going to exaggerate these arrows just a little bit to show that this arrow goes forever to the left and up, this one goes forever to right and up.
So before she writes down the domain and range, I want you to think about what the domain and range of this function would be as well. The domain, of course, lists our x coordinates that show up in the graph, and the range lists our y coordinates. What x coordinates will show up in this graph if it goes on forever, and what y coordinates will show up in this graph if it goes on forever.
So if we understand that, we could automatically say that our domain values continue forever to the negative numbers, forever to the positive numbers, includes all those fractions and decimals in between, so it is the set of all real numbers. Our range, on the other hand, describes our y values, which definitely has a limitation here. So our smallest y value is here at +2, but it includes everything that is above +2. So we could say that our range is the set of all y values where y is greater than or equal to +2.
Okay, so again, to say that our range is the y values greater than or equal to 2 would be just fine. We don't need the entire set notation here for our discussions in class. But hopefully you recognize that. The domain, again, all x values are going to be included in this graph somewhere, so we would say all real numbers is the domain of this function. And for the range, well, again, only y values that are bigger than or equal to the number 2 will be included in that list of coordinates. So I'm going to stop recording this other user's video right now. I think there are 2 or maybe 3 other examples. I would highly recommend that you watch through those and practice them on your own. But in the interest of time now, I'm going to switch over to my examples, and we'll continue through these for the rest of this video. Now for these next questions, we have to recall the vertex form of a quadratic. And if you recall, the vertex form of a quadratic function is something that looks like this. The function f of x is equal to a times x minus h, quantity squared, plus k, where the vertex, we would call the vertex, is located at h, k, that coordinate. So these two numbers represent the vertex of the graph, and notice that h is the opposite of what we would expect because of the minus sign here. And then we would use the a value to determine the shape, whether it's tall and narrow or short and wide, the shape of the parabola and its direction. Now in class, I try to emphasize when it comes to shape, it's either tall or short. We try to avoid phrases like wide and narrow because that's not truly an accurate description here. The a value adjusts the shape by stretching it taller or compressing it shorter. But it also tells us the direction that the graph will open in, whether the tails open up or open down. So one thing that I want to point out here with this particular function to begin with, okay, sorry about that. My dog just pushed his way into the room here and I got a little distracted. What I was saying is that we could rewrite this particular function in a more traditional vertex form if we recognize that there's an implied a value in front of this group and there's an implied k value at the very end of the group as well. So we could imagine that this function was written this way. And now we might note that the vertex is located at 4, 0. Again, it's the opposite of what we see here. And we have an a value of 1. So we now know where the graph is to begin with. 4, 0, that's the vertex, and it opens up at a standard height. So if I'm just thinking of a quick sketch here, here's the xy axes. 4, 0 might be right about here, and I'm not going to make a perfect drawing, but at least I understand that this is a parabola that opens up and is located here. Now if I switch pen ink to make this stand out a little bit more, we have another function over here, and again, if we think of how this is written in vertex form, we might consider it as 1 times x plus 4, quantity squared, plus 0. There is no number written after this, so we can assume that that's 0. Adding 0 doesn't change any values. That's the additive identity. But then in front, there was no number written, so we assume that that number is 1 because 1 is the multiplicative identity. 1 does not, or when multiplied, doesn't change the value of this group. But in this case, we have a vertex that's located at negative 4, 0. Again, it's the opposite of the h value on the inside, and it's precisely our k value at the end. And our a value in this case is also 1. So we have a parabola that opens up with a standard height and is located here at negative 4, 0. So this coordinate is here, this vertex is down here, and the graph is in this direction. So if we started at the black sketch and ended on the red sketch, we can see that this graph is essentially the same in both positions. We've just kind of slid everything from right to left. And so now, if I look at my multiple choice options, I don't think the graph moved up at all. I don't think it moved down. It did not move right. It actually moved to the left. So I think we can answer with C as a good choice here. Let's try the same with this second question. And we can use the same technique with this problem as well until you're really comfortable with these equations. Now, hopefully you do recognize this first graph is our parent function, so we should know what that looks like. But in case you don't recognize it, we'll say that y is equal to 1 times x plus 0 squared plus 0. If I were to imagine that there's a grouping symbol here, I could add 0 or subtract 0 on the inside and not change the value of x. And so that's why I can rewrite that section here. And again, there was no k value after that group, so I can write a 0 here, and no a value written, so I can write a 1 here. So this tells me that we have a graph with a vertex at 0, 0, and an a value of 1. So a standard height parabola opening upward, centered at the origin, is what we have here. But again, this definition, or this description I should say, is the parent function for all quadratics. We've talked about that one a few times. And if I were to sketch its picture, it would look something like this, centered at the origin and opening upward. Now notice here that this particular function was written with y notation. It would be exactly the same if we had used the f of x notation as well. Those are the same thing. So in this example over here, what would it look like in vertex form? Well, again, there's an assumed grouping symbol right here, but no number associated with the x inside that grouping symbol. So I can call that x plus 0 or x minus 0. I'm going to use the minus sign because it looks more like our original function, or our vertex form up here, rather. So we have x minus 0, and the minus 7 is on the outside, so that's going to become our k value, and we have an implied a value of 1. So this tells me that my vertex of this parabola is located at 0, negative 7, and we have an a value of 1. So again, it's a parabola that's opening up in standard height. it's a parabola with a vertex at 0, -7, which is down here on our coordinate grid. So we have a standard shape parabola that's been moved from here at the origin straight down to the new position in red. So we would say that this is a translation not to the right or left or up, but instead this has been a translation of 7 units straight down. Okay, so in this next example, which of the following is the graph of this particular function? So that's a multiple choice question, and we've got 4 to choose from, A, B, C, or D, which is none of the above. We should be able to spot this relatively quickly. This negative sign out front implies that we have an A value of -1, so that tells me that the graph is opening down, and it's a standard height. Standard height because the A value is 1. If the A value is bigger than 1, then it would be stretched taller. If the A value is smaller than 1, then, or I should say between 0 and 1, then it is going to be compressed shorter. We have a vertex located by the H and K values. So remember that the H is the opposite of what we see in the grouping symbol. So I'm going to say that the vertex is at -1, and the K value is exactly as written, -3. So we have a vertex at -1, -3, and the graph has to open down. So right off the bat, we can say that this is no good. That does not work. This one looks decent because the graph is opening down, but it's not located at the correct position. Instead, I think I would go with this one here. We have a vertex that's located at -1, -3, and it is a standard shape. I don't know why my ink keeps disappearing here. But I know it's a standard height because from this vertex I move over 1 in the x direction and then down 1 to reconnect with the graph. So over 1 and up 1 or down 1 would be a standard height. If I move over 2 units from the origin, if I move over 2, then I have to move down or up 4 units in order for this to be a standard height. And that does appear to be what's happening here in this particular case. So I would say, and I'm going to draw big arrows here in case the ink keeps disappearing behind that image. C appears to be the correct answer here. That graph represents what we've seen in our equation. Now 2 more just generic questions. Given that a function is in standard form here, now we're switching from vertex form to standard form, you'll notice. Given that the function is written in standard form and A is greater than 0, then what happens to the graph? Does the graph open up, down, left, or right? Well, it doesn't matter what form we're writing the equation in. The A value is the same in both standard and vertex form. And when the A value is positive, we know that the graph must open up. It's going to be a U-shaped graph opening up. Now therefore, if the A value is positive and the graph is opening up, then does the graph have a minimum value, a maximum value, at least one complex root, or is there no way to tell this answer without seeing the actual graph? Well, with complex roots, that's where we get imaginary number solutions. That occurs when we have a negative discriminant. We've talked about that in weeks past. I don't think that's really anything that we can answer right now. Some graphs do have 2 real number answers with no complex roots. Some have 1 real number answer with no complex roots. And some graphs have 2 complex roots. So I don't think that's really pertinent to this particular question. I don't think I would answer that here. But I can answer either A or B without looking at the graph. We know that if the A value is positive, the graph has to open up. And even if I don't know the A, B, and C values that specifically locate this graph, the fact that it opens up tells me that this vertex point is going to be a minimum value. So it has a low point or a bottom to the graph. So to finish out this video, let's go back to the beginning here and talk a little bit about the domain and range of each of these functions. And we'll do so by looking at the original function itself. So if I look at the original function here in blue, what do you suspect the domain is and what do you suspect the range is? Go ahead and pause the video now and resume playback in a moment to check your work. Well, hopefully you recognize that the domain is going to be all real numbers. This graph will stretch up and out, infinitely tall and infinitely wide. So any x value that we can imagine will show up as a coordinate in this graph at some point. The range, on the other hand, well, the graph does stretch infinitely tall, but there is kind of a boundary point down here. The lowest y value that we see will exist in this coordinate, and that y value is 0. So as long as we identify the range as all y values that are greater than or equal to 0, then I think we're in good shape. Let's take a look at this particular function, the one that's been translated here. What's the domain and range of it? Again, go ahead and pause the video now and resume playback in a moment to check your work. Well, this being a quadratic and the graph growing infinitely wide tells me that the domain is going to be all real numbers. No surprises there, hopefully. The range, on the other hand, well, it looks like all y values that are above this particular location will be included as coordinates. So we would say that y must be greater than or equal to 7 for our range. What about this function? What's its domain and range? Pause the video and resume playback in a moment to check your work. And so in this example, I would say the domain is, again, all real numbers. There were no arrows drawn on this particular graph, I think because it was generated by a computer, but we really should assume that there are arrows here. They are continuing this function in both directions. So the domain is all real numbers. And again, we're using this double bar r to represent all real numbers so that we don't get this r confused with this r. All reals, and this r represents range. Now, as far as the range goes, we're considering the y values that show up in this particular function, and I would argue that it's all y values that are less than or smaller than 3, or including the number, negative 3. All y values that are less than or equal to negative 3. Now, I can't ask that question for these last two examples because we don't actually have a specific location for this function. The domain, I know, will be all real numbers in both cases because that's always the case with quadratic functions. And the range, on the other hand, can't really tell that until we have a specific location for the start of this graph or the vertex point of this graph. So I hope that this video helps clarify some things and it gives you something to think about for today's class. There will be a Math Excel assignment active and available after watching this video and taking these notes. Please spend the rest of the class period working on it. Thanks for watching.